We are consistently told that artificial intelligence is modeled after the human brain. To actually understand deep learning, we need to break that metaphor. Relying on biological comparisons creates a false intuition of how these systems operate. Artificial neural networks do not possess cognition. They are not thinking entities mapping synapses. They are, at their core, strict mathematical optimization machines. The formal term is a function approximator. You feed raw numbers into the system, it subjects those numbers to a series of calculations, and it transforms them into a specific numerical output. To understand the mechanics of deep learning, we are going to build a mental model of a network from the ground up, relying exclusively on math and logic. We will isolate the artificial neuron, explore how activation functions create patterns, map the calculus behind backpropagation, and see how modern frameworks handle the equations. Real proficiency in machine learning requires leaving the biological analogies behind. It requires looking directly at the calculus underneath. The foundational unit of deep learning is the artificial neuron. Think of it as a tiny, isolated calculator. It takes an input value, x. It multiplies that input by a weight, w. It adds a bias, b, creating a combined output, z. The weight dictates the mathematical importance of the incoming signal. A higher weight amplifies the input's effect, while a lower weight diminishes it. The bias provides an independent adjustment. It shifts the output threshold left or right. This guarantees the node has flexibility, even if the input happens to be 0. A single calculation is limited. To process raw data, like the 784 individual pixels of an image, we stack these units vertically. This creates an input layer. The actual learning happens next, in the hidden layers. By adding dense columns of nodes, each subsequent layer combines the calculations of the previous one. The network learns abstract patterns. At the end of this dense web, the output layer collapses all of that multidimensional math into a single final prediction. We have built a deep architecture. Yet if you rely solely on multiplication and addition, weights and biases, the entire network acts as one giant linear equation. It cannot map the reality of complex problems. Look at this scatter plot. The data clusters form complex curved patterns. Because our network currently uses only linear math, it can only draw a rigid straight line. It fails entirely to separate the data. Real-world data, whether it is the syntax of language or the texture of a photograph, does not follow straight lines. It is messy and curved. To fix this, we pass the neuron's output through an activation function. This introduces curvature into the math. The current standard activation function across modern architectures is called ReLU, or Rectified Linear Unit. ReLU executes a simple operation. It outputs 0 for any negative input and passes positive inputs along exactly as they are. This creates a hinge in the calculation. Stack enough neurons together, and those hinges allow the network's mathematical boundary to bend and contour perfectly around complex clusters. Nonlinear activation functions are the exact mechanism that elevates a simple calculator into a system capable of sophisticated pattern recognition. The network makes a prediction through a process called the forward pass. Data moves from left to right, executing every calculation until an answer comes out. Here, the network predicts 0.8. The actual correct target is 0.1. To quantify the error, the system uses a loss function, measuring the deviation from reality. Knowing the error is useless unless the network can correct it. This initiates the network's actual learning engine, backpropagation. Backpropagation uses the chain rule from calculus to trace that final error backward through every layer of the network. It computes the gradient. This precisely isolates how much each individual weight in the network contributed to the bad prediction. It assigns the mathematical blame. Once the blame is isolated, an optimization algorithm, like gradient descent or ATOM, takes over. It adjusts the numeric value of those specific weights, nudging them slightly in the direction that will decrease the loss function. Step 1, forward pass. Step 2, loss calculation. Step 3, backpropagation. Step 4, weight update. The network repeats this exact 4-step cycle millions of times across the training data. Machine learning is not a cognitive process. It is a relentless, automated search for the lowest possible mathematical error. Modern networks have millions, sometimes billions, of parameters. Manually writing out the partial derivatives for a system that size is a practical impossibility for any engineer. This comparison highlights the solution. Deep learning frameworks, like PyTorch shown on the right, abstract the heavy calculus on the left into a few accessible lines of code. PyTorch handles the backpropagation math through a feature called automatic differentiation. Every time a forward pass executes, the framework silently builds a dynamic computation graph in the background. It maps every operation so it can perfectly reverse the math later. Engineers are spared the manual calculus. They can focus their time entirely on designing the network's architecture and tuning hyperparameters, like the number of layers. Translating complex optimization loops into accessible software is what pulled deep learning out of academic labs and turned it into commercial engineering. The math works, but only if the shape of the network aligns with the inherent geometry of the data. For structured information like financial spreadsheets, a standard feedforward network pushing data in one direction is highly effective. Images require spatial awareness. A convolutional neural network uses a sliding filter to scan a 2D grid, detecting visual patterns anywhere. For sequential text or time series data, recurrent networks and LSTMs use a self-referential loop, maintaining a hidden memory state of past inputs. These architectures require massive resources. To achieve high accuracy, deep learning networks need hundreds of thousands of labeled examples and significant computing power, specifically expensive GPUs, to run the optimization loops. They also suffer from a severe lack of interpretability. Tracing exactly why a million-parameter network made a specific medical diagnosis or credit decision is extremely difficult, creating serious friction for ethical and legal compliance. Deep learning relies on clear, rigorous optimization. Building a successful model demands understanding the data and designing a mathematical architecture that fits it perfectly.